You've spent a lot of time learning the rules and calculations of derivatives, and now we're starting in a part of the course where we're going to end up applying these derivatives or applying meaning to these derivatives. And in the beginning, that's a little weird because you're used to making these calculations. So we're going to give this a shot via video, but hopefully you'll have some follow-up questions later on. I'm going to use what I think is a pretty understandable scenario. We've got a boat, primitive boat, and it's got a hole in it. So the water is starting to leak into the boat. There might be a little bit of water in the boat already, but we've got a problem because water is going to continue to leak in. And we could model the situation, water flowing into the boat, in different ways. We could have a graph, we could have an equation, or we could have a data table. And the AP would ask you to interpret a derivative in this situation in any one of these formats for the sake of simplicity and for the sake of being able to visualize this a little bit better. Everything I talk about today is going to be with graphs, but realize it could happen from this or from this. So to get your brain thinking in the right direction, we're going to just start thinking about the scenario. If this were a graph of how many gallons were in the boat over time, and you were a passenger in this boat, you'd be feeling okay in this situation because as the minutes passed, the number of gallons in the boat is not changing. In other words, the water's really not leaking into the boat. Okay, life is good. Just keep fishing. In this case, now there's a little bit of concern. Maybe at time 0 there was a little bit of water in the boat, maybe a gallon. But as the minutes passed, the amount of water in the boat is increasing. It's increasing at a fairly steady or constant rate, but there's trouble happening here. The boat is filling up with water. Notice this thing has a slope. It's a constant slope. All right, well, if you're a pessimist, things could get worse. Look at this situation. I had the same amount of water in the boat as I did before, maybe a gallon when we started, but as time passed, the number of gallons in the boat increased, but notice the difference between this graph and this graph. Not only is the amount of water in the boat increasing, it's starting to increase more rapidly, and that's a problem. All of a sudden, when you start to see the curvature of that graph, you become more concerned because you can extrapolate out and say, wow, there's big trouble for me down in the future. So this curvature, by the way, as we talk more and more about second derivatives, this curvature is going to have to do a lot with the second derivative of x. We haven't talked too much about it yet, but we're going to need to start talking about it during this little scenario. Now let's start looking at these situations and start putting a little bit of calculus symbolism to it. Okay, so in this case, the case we weren't worried about, notice that the slope is 0, the slope is 0, so I could say the slope is constantly 0, or w prime of t equals 0. When I use a t, it means in general, no matter what t I select, my slope is 0. This situation was slightly more concerning because water was coming into the boat, and the slope is constant, but now it's a number that's not 0. So I could say the slope is always 4, or w prime of t is always 4. But now here's where we start thinking about a second derivative. If this slope is always 4, then the slope is not changing. Or in other words, the derivative is not changing. So the derivative always being 4 means that the derivative itself does not have a rate of change. The derivative is not changing. So the second derivative is the derivative of the first derivative, and since it's not changing, the first derivative is constantly 4, the second derivative is 0. That might have bugged you a little bit, but that is going to soak in over time. All right, now let's go to the concerning situation. As I go along this curvy path, the slope is increasing. The slope is 2, the slope is 3, the slope is 5, the slope is 7. Now remember, I'm talking about the slope or the slope of the tangent line. I'm not talking about the y value of the graph. That's a totally different story. This slope represents the derivative. So what I can say is the derivative is changing. So I have some statements written over here. You can see that the slope is changing. So you could also say w prime of t is changing. That's saying the same thing. Thus, the slope has a rate of change, or w prime of t has a rate of change. Okay, anytime we're talking about the rate of change of the slope or the rate of change of the first derivative, we're really talking about the second derivative. And so when we do this second derivative, which is the derivative of the first derivative, it means something. In this case, the second derivative is positive because my slope is experiencing a positive rate of change. Again, I know this could be a little bit troublesome for the brain. We're going to now look at what would happen if we were to take an actual derivative value and then do what the AP is going to ask you to do, which is interpret the meaning of a derivative in context. And so you'll see as you go through homework examples and you check your solutions that a good answer, an AP style answer to this, is going to have units, context of the situation, and specific numbers and or symbolism from the situation. So we'll look at this first one. This is the case where the water was coming into the boat and the derivative is constantly 4, but that's okay. We're only worried about this spot right here, and I'm just telling you that w prime of 10 equals 4. And so in an AP style problem, they would say, interpret the meaning of w prime of 10 in the context of the scenario. And so you would say this: 10 minutes after the leak began, by mentioning the 10 minutes, I'm acknowledging the 10. The water in the boat is increasing at a rate of 4 gallons per minute. That 4 is matching up there. That 10 is matching up there. And then the context of the situation is that the water in the boat is increasing. It's very good to use the word rate because we're interpreting a derivative, and a derivative is a rate of change, and they always want units. So I need to say 10 minutes. Minutes are a unit. And then how are we measuring this 4? This 4 represents gallons per minute. You know that either from the context of the situation, or you might know it because this is a derivative. Derivative is slope. Slope is change in y over change in x, and the y units and the x units, y units and x units. Okay. This is a picky and clunky sentence, but you have to be able to write this sentence to describe that meaning. And if you do that, you're going to get easy points on the AP test and have a genuine understanding of the situation. I think you would like that question on the test, and you'll eventually like this question. It just depends right now on how comfortable you are with the second derivative. So we're going to take a look at a second derivative interpretation. Okay, so we've been given these values, so don't worry about how we got them. And we're now going to interpret the second derivative at 10. Well, the second derivative is talking about the rate of change of the rate of change. So at 10, my rate of change is 4 in this case, which means the slope of that tangent line is 4. But now this thing tells me, w prime of 10 equals 2, tells me that this slope is increasing at a rate of 2. I'm not going to say the units yet, but it's increasing at a rate of 2. The fact that w prime of 10 is positive tells me that this slope is trending towards a greater slope, a greater slope, a greater slope, a greater slope. If this was negative, then over time we'd be trending towards a lesser slope. So when I write my answer, interpreting w prime of 10, well, I have to interpret 10, there it is, w double prime of 10, and the 2 is going to show up there. And now I'm talking about the second derivative, which is the rate of change of the rate of change. So we're talking about an increasing rate of the rate of water entering the boat, i.e. K COSA. And finally, I need some units on here, and we're going to show these a little better in the next example, but since the rate on the derivative was gallons per minute, the rate on the second derivative is gallons per minute per minute. Those of you in physics have been down this road before. Let's take one more look at a second derivative. If this is bugging you, it's going to get better over time. Hopefully this one's not bugging you. So here's a common thing that you'll grow used to with the AP. Sometimes they'll give you a graph, but as you look at the situation, the graph represents a rate. So even though this doesn't say derivative, it represents a rate of change, which really makes this thing act like a first derivative. So if you were asked to interpret r prime of 10, well, since this is a slope of 0, r prime of 10 equals 0. So 10 minutes into the leaking scenario, the rate at which water is leaking into the boat is not changing. They usually wouldn't ask you to interpret something that has a value of 0, so let's look at something a little bit deeper. Hey, no pun intended on that one. We have a graph of r of t. R of t is the rate in gallons per minute that the water is coming into the boat over time. So if the derivative value here is 2, that means the rate at which water is coming into the boat is actually increasing. So not only is water coming into the boat, but it's coming into the boat at a greater rate here, and even a greater rate here, and even a greater rate here. So that could be trouble. Well, if I had to interpret r prime of 10, here we go. 10 minutes, the value is 2. My units are gallons per minute, gallons per minute, and the tougher part is what's happening here is the rate at which water is coming into the boat is increasing at a rate of such and such. So the rate of change is experiencing a rate of change. Okay, so this is new and possibly clunky for your brain. Give it a shot. There's a note sheet on the lesson plans. There's also homework with written solutions. The more you look at these, the more they'll start to soak in. If you have despair, know that if you're good at this one right here, you've got a good running start, and over time, you'll get better at second derivatives. And in the next coming weeks, I think we're going to go in depth on what this second derivative means to graphs. See ya.